watch about your jokes if you're going to say something bad about Trump. Yes.
All right, great. Is that good? Okay. All right, well, thanks very much for the introduction, and it's a pleasure to be here and to see the sun on this day, which is, I had the belief that this was a center of rain. So, I want to encourage questions as we go through. I've allowed plenty of time for questions, and I think it's worth doing that for this, because one thing that I'd like to do is kind of explain a bit of the interaction with device physicists that occurs for these systems. Because you may read these proposals in journals where people say, well, we have this nice new physical effect, and presto, we have a device, and this device is fantastic, and will outperform every other device. And you may try to explain this, for example, to somebody who makes devices for a living, and at some point they stop listening to you. You don't know what you said. So I'll try to give you an indication of what might be happening there and what they're worried about and what is the underlying set of assumptions that guides this. So this is work that's done with particularly Junaid Shaheen, who's now a postdoc at University of Utah, Joost van Bree, who's at University of Chicago, Andrei Silov and Paul Kunrad at Eindhoven University of Technology, and more recent work, not going to talk about it so much, but with Jianping Wang at Minnesota, Nitin Samarth at Penn State, and Mingxiang Wu at Colorado State. The work on topological insulator spin Hall conductivities appears here. This is work on dissipationless spin currents, and this is the device treatment, and the work is supported by the Air Force Office of Scientific Research and also CSPIN, which is one of the 6 StarNet centers the Semiconductor Research Corporation has established. Okay, so this is a common type of plot which talks about Moore's Law, and we want to think about where we might go after Moore's Law stops. So let me put this into a bit more context. You can see the darker blue line is the number of transistors per unit area. The lighter blue line is the clock speed, and the grayish brown line is the thermal design power. And if you look at this plot, you'll see that it naturally separates into 2 regions, and this is in fact how the semiconductor community views this. The first region is what they would call scaling, and that goes up until 2000. And this was a magical time when you would make the devices smaller, and at the same time they would go faster and they would take less power. So it was a gift from the heavens, right? And that stopped right around 2000, and we are now in the region that they would usually call beyond scaling, where you continue to put a smaller, continue to make the transistors smaller and smaller, but they do not get faster, and they still take the same amount of power. So this is a limiting behavior, and you may have noticed, some of you, actually I don't know, how many of you remember when it seemed like the clock speed seemed to go up every 6 to 12 months? Yeah, so identifying the older people in the the rest of you, it's like 3 gigahertz. That's what it is. It's always been 3 gigahertz. We never get any better than that. Well, that's because this is where we are. And so this is an issue because, in addition to not improving that kind of performance, at a certain point you're not going to be able to put more transistors on a chip. There's a bit of an advantage to putting more transistors on a chip just in terms of space, but it's not in terms of performance. Okay, so what kind of perspective might we take on this? I'm just going to pick on this particular publication because, I could have picked on a variety, but I'll choose this one. Okay, the end of Moore's law, blah, blah, blah. When do you think this appeared? Okay, 2000. All right, and this is great for these publications because they can then recycle this and publish basically the same article 16 years later. It's where we are, and well, this actually appeared. Okay, so here's my joke, right? So this appeared before the election when this was still funny. It's now not exactly funny, but yeah, can the White House make America's chip industry great again? Oh God. Well, this died right after the election, right? So all the prospects of this went out the window. But we can still worry about these features. And then this is another plot that is kind of attractive feature to look at, especially when this is the initial, the left-hand side is when the prediction was made, and the right-hand side is when Moore's law was predicted to end. And so, these are roughly 10, 20 years. And what's additionally amusing is you can look at the number of times it went back to Moore. So they asked, 1995, and he said, oh, well, 2005. They asked him again in 2005, and he said, oh, 2015, 2025. They asked him in 2015, it's like, yeah, 2025. So, it's a continually revising feature. And a lot of it comes down to what are you asking? Are you asking if scaling is going to end, or are you asking if Moore's law is going to end? And the most generous interpretation of Moore's law, which is the number of transistors, that's still happening. But scaling is over, and it's been over for 15 years. And that is actually why the semiconductor industry really wants to find new solutions for devices. Okay, so why spin? This is a plot from an article about 15 years ago, and it shows a artist rendition of a proposal about 25 years ago, which is one of the first proposals to use spin in a quote device, unquote. And so this is an example of a device that, especially the semiconductor device community viewed as not really a device. And so in order to analyze how spin might help you, I'm going to show you a different type of device that is easier to treat. I mean, the basic concept here is good from a physics perspective, or from a device performance perspective, a little problematic. The physics picture is that you have an applied voltage here, so this is your thing that looks like a gate, and if you inject spin-polarized electrons and they propagate along in spin-polarized current flow, then for one setting of the voltage, those carriers can happily move into the drain on the other side. But if you set it differently and you rotate the spins due to a Rashba type effect, then you can't inject those into the drain and you end up with a higher resistance configuration. Okay, so it sounds good, right? High and low resistance. The problem is if you increase the voltage still more, then you come back around and you get high conductivity again. So this device has no saturation, and that kills it from a device, from a transistor perspective. So again, let's take a simpler system. And this is something that is sometimes called a spin lifetime transistor, but it doesn't work by coherent manipulation of the spin. It's entirely incoherent. And so what I'm showing is a source and a drain, source on the left, drain on the right, and band edges corresponding to spin up and spin down. Spin up is the green, spin down is the red. And so if you look at the top here, a spin down electron cannot move through this barrier. You only get spin up. And on this side, a spin up electron can't move through, you only spin down. So it's kind of like the cross polarizers arrangement. And if the spin lifetime in the channel is very long, then you don't get any conductivity. Now, if you can change the spin lifetime in this, then you turn the device on and you get conductivity. So that's the high resistance, low resistance configuration. And so this was really the first device that was analyzed in a in a serious treatment by the semiconductor community in this work by Tom Tice and Paul Solomon from IBM Yorktown. And their concession that this, in principle, was a superior device was very helpful to generating support for spin physics in the semiconductor community. Okay, so this is the basic functioning of the structure, but the question is, why would such a thing have a low voltage threshold and a small capacitance versus the typical transistor devices? And this item down at the bottom, the small subthreshold slope, that's a bit of a technical term, but it indicates how much voltage it takes to turn something on or off. And that is, in current CMOS, it's about 60 millivolts per decade, so smaller is better, because it means you have a smaller threshold voltage. Okay, so physically, how do you change the spin lifetime from long to short? And here again, you can use the Rashba fields, and just the presence of those Rashba fields will cause the spins to decohere, to relax to the other spin direction. So this is an example of a 110 grown quantum well, where the spin orbit field without an applied electric field is out of plane. It's indicated by the blue. But if you apply an electric field to the system, you generate this fluctuating effective magnetic field that is in plane and causes a spin that's polarized out of plane to relax. And the amount of relaxation that you can get is quite substantial. For electric fields that are on the order of some tens of kilovolts per centimeter, you could change the spin relaxation time by 5 orders of magnitude, which is the kind of thing that you'd like to do. And if you turn this electric field into a voltage, you get a rather small voltage on the order of 100 millivolts, which is quite a bit smaller than CMOS threshold voltages. Okay, so why so small an electric field? And the reason is that if you want a 10 picosecond spin flip rate, that corresponds roughly to a spin splitting of 4 millivolts, which is much less than KT. So you do not need to change energies by anything compared to KT in order to change the behavior of the system, to turn it on or off. Okay, and so in a comparison between this kind of device and an ordinary CMOS transistor, where you have to raise a barrier, which is typically 400 millivolts, or lower it in order to turn it on and off, the voltage that you need to apply is a lot smaller. And this works by electric field rather than density accumulation. So the capacitance, ideally, is very small. That means the energy required to run it is very small, several orders of magnitude smaller than CMOS in principle. Okay, and just a brief, I guess I won't show that. Okay. All right, so why voltage? Why not current? So what's the speed for a change in voltage to propagate from the drain of a transistor to the gate of the next? This is a candidacy exam kind of question, or qualifier question. Any students? Extremely fast. When I was a student, my advisor, Walter Cohn, told me at one point, you need to give me a dimensionless parameter. So what's your dimensionless parameter? So relative to what, right? Fermi velocity, okay. So now the, what? Speed of light, okay. So these are two answers that differ by a factor of 300. Got a vote? How many think speed of light? How many think Fermi velocity? Right, okay. So you might think diffusive transport is the drift velocity of electrons, which is essentially this response. By the way, this was a subject of considerable fights in the electrical engineering community in the 1980s. And so there were fundamental arguments, applied arguments, but the connections between transistors are essentially transmission lines. These are these copper wires that are between them. And so the signal is propagating as it would on a transmission line, essentially at the speed of light. But the community was not convinced of this until they did a direct electro-optic sampling of the transmission in integrated circuits and saw that that was the speed. Sorry? Yes, well, everybody passes the exam, right? We're not going to flunk the organizer. Who also has the advantage that he was brave enough to make the first statement. Okay. The other thing is that voltage offers a natural approach to fan out. So if you have a voltage, particular setting, that means that everything that is connected to that by metal is going to have the same setting. So that is an advantage. So you really want, in principle, to use voltage and spin transport and only use charge in situations where you have very low capacitance, which means that you're going to use electric field rather than electron density effects, similar to, as I described for that spin transistor. So that means you're going to be working either with coherent spins that will be where their relaxation might be controlled, or some kind of collective spin motion. The case of the spin transistor, this is essentially working with coherent spins. In the case of topological insulator switching, it's more collective spin motion. Okay. Absolutely.
Is this a crucial issue for being useful, that the speed of light, namely 100 times slower but not be fast enough? Is that something that spintronics is kind of fundamental thing to worry about? You can do things in spin signals rather than electromagnetic signals?
Is it it is certainly the case that if you're going to compete in digital electronics, then that's going to be a major problem. Because one of the advantages you get by shrinking the transistors is making the communication speed better. But possibly a more critical issue is this one of fan-out, which is figuring out how much it's going to cost you in order to have the same setting on 5 or 6 gates down the line. There certainly are plenty of devices that do not really care about the speed. And there's a whole other direction where spin appears to be beginning to play a major role, which is in very low power but slow devices. So when you think about the Internet of Things and you have millions of sensors that you want to take, you want to have microscopic batteries or work on solar, you need to have exceptionally low power consumption, and that's a place where spin plays an important role. Okay, so why topological insulators? And I have to admit that part of the reason for taking a look at this had to do with, yes? Yeah. Yeah, so if you have a pulse, it will travel along that transmission line at the speed of light. No, it's a wave. The whole point is that it's a wave of voltage, and the electrons themselves are not moving from one side of the wire to the other side of the wire. Yeah, it's like the water in the ocean. The wave moves with a given speed, but the water is not moving from Hawaii to here. The water stays. Yeah. Well, R is nearly negligible. It's an entirely LC. Yeah, I mean, it's going to be limited by the LC feature. And in fact, the energy of the interconnects is completely unrelated to the resistance. From the perspective of this, the resistance is essentially unimportant. The energy dissipation is entirely from the capacitive charging up of the wire. And this is another design issue, because if you want to push things towards directions where you have very, very low capacitance, then you also have to solve the capacitance issues with the wires. And so this is something that is already under investigation, where these vias, first they switch from aluminum to copper, then they have, now the copper is going to be in some kind of vacuum gap as opposed to another kind of dielectric, again, to reduce capacitive charges, capacitive energy dissipation. Other questions about? Okay. All right, so this is a relatively famous paper suggesting that there is a very large spin transfer torque that you can generate from a topological insulator. And leaving aside some of the arguments about the interpretation and the other aspects of this, it is the case that measured spin Hall conductivities in these systems appear to be quite large for correspondingly small longitudinal conductivities. So this connects to something that's called the spin Hall angle that I'll get back to later on. And from my point of view, from my group's point of view, we wanted to look at this because we had been thinking about spin currents and dissipationless spin currents, but not really in topological insulators. And so now let me tell you a bit of a story, but it'll appear a bit of a digression to begin with, but I'll bring it back to topological insulators later about dissipationless spin currents. And our motivation for looking at this was trying to understand the magnetic moment of electrons in semiconductors, which is a problem that, from a mathematical perspective, to an extent was solved 50 years ago, but sometimes it is helpful to get additional understanding of what's happening by looking at some previously unexplored features. So here's a bit of the motivation for this. You might say, well, if I ask what the magnetic moment of an electron is, I can think of it as a free electron. I can think of it as an electron circulating an atom, and I have certain ways to calculate those G factors. I can think of it in a bulk crystal, a semiconductor crystal or a nanostructure, and in some ordinary semiconductors, like indium antimonide, the G factor is in excess of 50. That is some kind of reflection of the magnetic moment. It's telling you the magnetic moment is 25 times larger than it would be in a free system. And so you can take a look at where this comes from by calculating a spin correlated orbital moment. So this change in the magnetic moment has to be coming from some kind of orbital motion that is then coupled to the spin by the spin-orbit interactions. That's a spin-correlated orbital moment. And you can calculate this directly in this kind of fashion by basically doing a direct calculation of the current for the system. So you should be able to see the current of the system. And let's say we take an L equals 1 system. We would have orbital angular momentum, perhaps of -1 or +1, corresponding to some circulating current going around one way or going around the other way. And that will give you a change in the moment to a degree. But for a G factor of 50, you start wondering, what does this mean? Do you have a wave function of e to the 50 I theta? You certainly do not. So where is it physically coming from? So where's the current? How does it produce the magnetic moment, and how is it affected by confinement? And I can already tell you, and I hope you will believe, that it has to be a dissipationless spin current that's causing this, because it's going to be spin correlated, it's going to be orbital, and it's the current in a state. So the state exists, it has a given current that is built into it, it can't dissipate. All right. So for this, we can take the analytic solutions for electron states in a ordinary sp3 tetrahedrally bonded semiconductor, so an 8-band model, in spherical confinement, And it turns out that there are analytic expressions for this, but for whatever reason, the currents associated with these were never calculated. And you generate an 8-component combination of spinor and orbital indexed wave function, where you have conduction states. So this is the conduction bulk band spin up, conduction bulk band spin down. These are heavy hole, light hole. It's the other heavy hole, and these are the split off. And you can see it's composed of spherical harmonics. The lowest energy state is going to be spherically symmetric for the conduction envelope function. But in order to conserve the right orbital momentum, since the block function has orbital angular momentum, the envelope function has to have the opposite angular momentum to compensate. And so that's this contribution here. So when you follow that through, what you find is that for the conduction state, spherically symmetric spin up, for the valence states, these are L equals 1. So they are envelopes that are circulating around and carrying the current around. So that's a direct cause of this kind of dissipationless current. Okay, so then you can just calculate this current directly from the expression that we have for the current using the block functions, which are the U's, and the envelope functions, which are the F's. And you get what you see here. So this is for spin pointing up on the board, and this is current coming out, current going in. So the current, that orbital current is circulating around, and you get a magnetic moment that's also distributed in space in a rather peculiar way. So again, this is the lowest energy state of an electron in a spherical quantum dot, and it has a circulating current if the spin is oriented in a particular direction. So how does this relate to topological insulators? So let's compare. So here's our typical insulator. We have our S bands and our P bands. So the S is on top here, and P is down here. So you have 6 of these and 2 of these. And the energy of the state that I've been talking about with the circulating current is just above the conduction band minimum, because it's a confined state in the quantum dot. And so this is a system, it's an insulator because it has a full band, but it also has the case that the spin and orbital combinations below the Fermi level are all balanced. So when you go to a topological insulator, you have a different configuration. So let's start with band inversion. So we're putting the J equals 3/2 states up above in energy, and the split off and the conduction states, S states, down below. However, this isn't balanced. I don't have 6 down below and 2 up above, so I need to fix that, and the way I fix that is by adding confinement, okay, which moves 2 of the ones from above down below. And so now I have an unbalanced spin-orbit correlation that's filled. And this constitutes, this behaves as a topological insulator. This is essentially confined mercury telluride or many other such systems. Okay, once I have that unbalanced spin-orbit correlation, then I can take a look at its properties. And so this is what's motivated quite a bit of the work on topological insulators. You can see this combination down here. This is the essentially that unbalanced state, heavy hole state, and then down below you have what is the split off confined light hole state. And the surface states form in between. They form in this gap over here. Okay, so now let's bring it around. We know that topological insulators have these spin-correlated edge states that sit at the chemical potential and in the gap. And how does that relate to our circulating currents in the conduction states of the dot? And the answer is that these circulating spin-correlated orbital currents are now pushed to the edge in the topological insulator system. So they are identical in origin. They just occur at the chemical potential for the topological insulators because you have this unbalanced state configuration. Okay, so now let's take a look at the spin Hall conductivity for some trivial and topological insulators. And as a good starting point, let's look at the case of bismuth-antimony. So this is an alloy that goes from pure bismuth. Yeah. Yes.
Of the topological insulator, right? So yeah, so in the toughest state, the topological insulator is unstable against the magnetic field. Right? If you apply magnetic field, surface state is removed. So what
Correct.
happened for your spin correlated current
For these,
in the magnetic field?
right. So it is not the case that the spin-correlated edge states of the topological insulator disappear necessarily in the magnetic field. It depends on sort of what you've done. If you have a ferromagnetic system, then you will gap them, and so they will move to a different energy. So now they'll be above the gap or below the gap. If you haven't gapped them, you will say you just apply a magnetic field, and so you spin split them. They still are there, they're just no longer topologically protected, so they can scatter one into the other. So the properties of the states are robust. This is the argument I'd like to make, which is that they're there, whether it's a trivial insulator or a topological insulator. It's just a question of what energies they reside on and what level of topological protection that it is present. Yeah.
So this picture, so the picture that you have there with the spin current, so can you measure this? Is there anything, put like a tip and measure actually the spin?
I hope so.
Is strong enough like the current? Or?
Well, yeah, I mean, the size of the the size of the feature is substantial. So it's a question of the size of the dot, and
so you can map out experimentally if you move with a spin polarized tip.
In principle. So one thing I haven't shown from this is that this manifests itself in a spatially dependent magnetic moment. So another question you might ask is, I have an electron in the ground state of the quantum dot. What is the magnetic field that you calculate from that? And I think most people would say, well, I have some probability density for the electron distributed throughout the dot, and I just take that and I put in the effective G factor, and I calculate the magnetic field from that. That's what I get. That's not right, because in fact the magnetic moment is spatially distributed in a let's see if I can find the here it is. Yeah, so the magnetic moment is spatially distributed in this fashion, which means that if you could bring a magnetic field sensor close enough to the dot, you should be able to see the difference between this kind of distribution and the trivial distribution that you might expect. It's a hard experiment, but I'm not an experimentalist, so it's less my problem. So what I'm plotting here is the magnetic moment coming from the itinerant current through the dot and the block velocity. So this is the biggest contribution to the magnetic moment. fact, in this in the PhysRev B, we calculated all these different components to it, and it sort of depends on the size of the dot, but most of the time those are very small compared to this dominant feature, which is the itinerant current running around in the dot. Well, so when you calculate the current, you know, the expression is up there with the full wave function, and so you'll get contributions from the block states. You'll also get contributions from the envelope functions, and so we've calculated both of those. The envelope functions are huge by comparison, and the reason, well, it depends what you mean. So let me. There's a terminology that we've introduced that may or may not be so clear, but you know, here, for example, you can see two different components. This is block times block with envelope function, gradient of envelope function. So this is really coming from the derivative of the envelope function, and this is very small. This here involves a gradient of the block function. That's the big term. That's why we call it the block velocity term, because it's block velocity. And then this is a combination that is, say, conduction. So let's say I is conduction and J is valence. So this is envelope L equals 0. This is envelope L equals 1. And so this is the big contribution, and then this is the product of something that is spherically symmetric and something that is running around in a circle, and that's how you get these itinerant currents. Okay, any other questions about the secret lives of dissipationless circulating currents? Doesn't like moving so quickly. Okay, there we go. Okay, so this is a nice system to look at because there is a continuously variable electronic structure from bismuth to antimony. Bismuth and antimony are both semimetals, but in between, for a range between 9% and 22% antimony, the conduction in the valence band cross, and you have a topological insulator. The electronic structure for bismuth-antimonide is pretty well known. There's a type binding parameterization that is that people are reasonably confident of. And so we can just directly calculate the spin Hall conductivity for this system. Okay, so let's take, for example, 17% antimony. And so you can see in this system that there's a nice gap. Something that looks like a big pseudo gap. The gap itself is very small. It's only on the order of 10 or 20 millivolts, but it's in there. And then you directly calculate the spin Hall conductivity from the Berry curvature of the filled states. This is why having the unbalanced spin-orbit correlation is critical to getting the topological insulator in a non-zero spin Hall conductivity at a topological insulator that is not longitudinally conductive. That Berry curvature is related to spin current velocity correlations, essentially. And a convenient way to write it, one that we like, is to write it as an integral over the filled states. So F there is the Fermi function. times a density of curvature. This is something that was done for metals in 2008 by Gua, but we use it for this system as well. And here's a plot of the density of curvature. And so you can see it has features that are related to the spin-orbit correlation. And so it has one sign below the Fermi energy, and it flips above. And because it's a multi-band calculation, there are quite a few other oscillations. But if you were to go very high in energy, it would balance out, or very low in energy, and it would balance out. It's sort of in the middle, that it doesn't. And because you're at a band gap, it's zero, precisely energy zero. But the real question, unlike an ordinary conductivity, is you're summing over filled states, as opposed to only summing over kT near the Fermi energy. So this is a filled band contribution to the spin Hall conductivity that is non-zero. Zero temperature. I mean, we've done it for other temperatures, but let's just look at it at zero temperature for this. Yes. Well, it is in reasonable agreement with DFT, but there's a high-quality tight binding parameterization from the mid-90s by Phil Allen that we use. And in fact, there's also, I'll talk a bit about the parameterization and how unimportant it is, because there was a big fight over precisely what the band edge properties were. And so there was another parameterization that was produced in order to fit the band edge better. I'll show you what effect it has. All right, so the first message is, here is the spin Hall conductivity at the chemical potential as a function of antimony concentration. And I defy you to pick out, this over here is, so the axis this way is the spin Hall conductivity, and this is the concentration. So I defy you to pick out the transition points between topological insulator and semi-metal. And, well, you can, because I've indicated them by the dashed lines here. So you can see there's a huge effect of that transition on the spin Hall conductivity. Right? No, right. You're shaking your head because there is none. So let's blow that up. So this is now blown up from 472 to 488. So I've blown up, about 2% of its value. And so you can see how it changes as it goes across. There's practically no non-analyticity. The red is the 1995 parameterization by Phil Allen. The blue is a later parameterization to get the band edge properties right by Teo et al. And so there's essentially, it doesn't care at all about what's happening at the chemical potential. It's entirely determined by the filled bands of the system. And that's good, because if I want to do anything with topological insulators and voltage control, I want to get as far away from edge states as I possibly can. So from this point of view, the key feature of topological insulators is that they have a full band bulk contribution to the spin Hall conductivity that I wish to use. Okay, what about the spin Hall angle? Spin Hall angle is the ratio of the spin Hall conductivity to the longitudinal bulk conductivity. And this is the thing that should be very different, because the longitudinal bulk conductivity in principle in the gap goes to zero. And so I go from a finite spin Hall angle to an infinite one, and then back to finite. So this is a bit of an explanation of why you can get such large spin Hall angles in the systems. It's not because you have such a huge spin Hall conductivity itself. It's not necessarily larger than many other systems. What's really key is that you have a very small longitudinal conductivity. That's what you really want. And that's also good if you don't want current flow, if you want to work with voltage. All right, so now we approach the device. So here's a picture, a cartoonish picture of a device where I've got contacts, the voltage applying contacts, so it will apply an electric field across the system, across this large spin orbit material. Let's not necessarily call this spin Hall topological insulator yet. Then I have a large voltage, and then I turn it off. So in principle, I apply this voltage, I generate an electric field from the bottom to the top, and that causes a spin current to flow due to the spin Hall conductivity. So I want a large spin Hall conductivity to generate a large spin current to flip this magnet. I want as small a longitudinal conductivity as possible, and I want to get rid of or avoid in some way the highly conductive edge and surface states that are essentially sinks of spin polarization at the interface. So the whole thing of working with high-speed interconnects, dissipationless spin current type things, I don't want any of that because that's going to sink any kind of spin polarized chemical potential or spin density at the interfaces. So I'll talk a bit about how one does that later. But first, let me justify this a bit and connect it to another system that we know and love. So, what does it mean to be working with a system that is insulating in the bulk, but that has a finite spin Hall conductivity? And a good way to get a picture of this is to think about the quantum Hall system in a Corbino geometry, where you don't have the edge state connection. So this takes you out of the edge state perspective and puts you back in the more bulk perspective. So what's happening as you run magnetic flux through the center of this geometry is that you generate an electric field that is circulating around. That electric field changes the phases of the wave functions of the band and effectively moves electrons from one edge to the other. So it is a purely collective effect that is related to the Berry curvature of the system. And again, quantum Hall system is a case where you have a full band which has a finite Hall conductivity. Okay, and this expression here, which is nearly identical to the expression that I've been using, is the expression that that is used to talk about the Hall conductivity and its quantization. In fact, that's where the 2016 Nobel Prize came, as the relationship to this theoretical observation that you can talk about the system this way. Okay, so what's our Corbino geometry going to look like for the spin Hall system? Let's make it as similar to the quantum Hall state as possible. All right, here we go. So in this situation, when you run the change in magnetic flux through the center, you produce that circulating electric field. The response of your full band is to move spin down electrons towards the center, spin up electrons towards the outside. And so you generate a spin density splitting as a result of this. And you do that until the point where the density becomes enough to exceed the gap, and then you get backflow. So there is a limiting feature to this in principle. And as again, in this geometry, the edge states don't sink the spin polarization because you are not connecting the spin up to the spin down accumulation. All right, and we're using this expression where it's a different curvature, but very similar in concept to the quantum Hall system. All right, we don't necessarily want to make our devices in the Corbino geometry. That sounds hard. I think Corbino is one of those things that semiconductor device physicists are allergic to. So you could, for example, imagine magnetic doping, where you generate a ferromagnetic state near the edges, and so you gap the system. And so you have localized states near the edge. Those localized states end up being filled by the accumulation of spin at the edge. There are other approaches where you sandwich your magnetic insulator between two topological insulators, which is probably pretty hard. Okay, so here's kind of the picture of what you would have. You've managed to kill the edge states. You have a voltage applied across the system which generates an electric field. In principle, you have this longitudinal current, but you're using a topological insulator, so that longitudinal current goes to 0 because there's no longitudinal conductivity. It causes a spin current to flow that is associated with the full bands. That spin current remains even though the longitudinal current is not there. And then you have other features that will degrade the accumulation. You have recombination at the edge, you have diffusion back, and so on. So what kind of accumulation rate can you expect for spins at that interface? Well, you can put in expressions for already measured spin Hall conductivities in systems like bismuth selenide, and you get rates that look like this. So it's actually quite a rapid rate. And this is now the switching voltage measured in volts. We're going to take a low switching voltage, so the capacitance of the wires makes a small contribution to the switching energy. This is sort of a tricky way to avoid the capacitance issue, and it's why the threshold voltage is important in analyzing performance. And so if we take a 50 millivolt switching voltage, the energy is 100 times smaller than in CMOS, which is a good starting point. What about the effect on a magnetic insulator? Let's base the switching on YIG and assume you have polarizable localized surface states. And so you have a certain number of non-equilibrium spins that are going to interact with the spins in the YIG through an exchange interaction. You can use the effective exchange interaction in YIG as a gauge for how big that effect is. Exchange field in YIG is about 100 Tesla, 20 spins per nanometer. So per nanometer, that gives you about 5 Tesla. So this gives you a size of an exchange field, which depends on the thickness of the magnetic insulator, so thin is better. And so you can convert that to a frequency, and that gives you a switching frequency that, when you consider the accumulation of spins and the effect on the YIG, and you say, well, let's say that half of the time is spent accumulating and half the time is spent processing the magnetic insulator's magnetization, you get a switching speed that's on the order of 600 gigahertz times the square root of the switching voltage in volts, and an energy that is essentially associated with charging up the capacitor, which is the topological insulator region. So that gives you a rather remarkable result of 100 gigahertz for the switching rate and a switching energy of about 10 millivolts as an ideal behavior. 5 minutes? Okay, that's fine. So, there are also going to be other degrading effects on the device, which can limit this, but it's good to start from a situation where your ideal performance is quite good, because there are always going to be things that you haven't worried about. Okay, what about things like recombination? How much does this change things? Well, if you have recombination at the edge, some kind of spin scattering, let's say that your spin lifetime is 1 picosecond. Well, you have to measure that relative to the 200 terahertz of the accumulation rate. And so it's a negligible effect on the rate and the energy, even if your spin relaxation is a picosecond. Okay, so for highlights of this, I've talked about how spin orbit effects produce circulating currents for excitations both within bands as well as within the band gaps of topological insulators, how the spin Hall conductivities are associated with full band characteristics. They're not, the edge state picture is not the most useful picture perhaps to look at spin Hall conductivities. It's really the full bulk picture, like one can also use in the quantum Hall system. And the key point is that these are collective features of the full band, so you don't need carriers to talk about the effect. And not needing carriers is great because it means that you do not have that form of dissipation. So spin Hall conductivity really is a collective property of a filled band and an indication of circulation within that filled band. If you can kill the parasitic effect of longitudinal currents into edge states, say in the Corbino geometry, you can definitely get voltage-driven magnetization switching with very low switching energies, capacitance, and switching, and very fast switching speed. Spin relaxation, even if it's fast, isn't a significant impediment, but there is going to be further energy dissipation expected from magnetization dynamics. So thanks for coming with me on this long journey through device physics and topological insulators, and happy to answer any other questions.
Thank you.